Today we have a short examination from the flow kinematics in fluid mechanics. I have written 10 questions on the board. The first question, is about the continuum principle, and I've asked if this velocity field is continuum. As you see, we have the dimensionless velocity here, which is defined as the ratio of the velocity component and the velocity of the upper wall. This is the flow between two parallel plates. The lower one is stationary and the upper one moves with the velocity of v. And this one is the dimensionless vertical coordinate, which is the ratio of y and h. H is the distance between two plates. So, is this velocity field continuum? The second question is about the dimension of the flow field. This velocity field is written in polar coordinate. This is the circumferential velocity, which equals a constant over squared x plus squared y. And the radial component of the velocity is 0. What is the dimension of this velocity field? Exactly a similar question for this velocity field. We have the horizontal velocity equals x over t plus t sub 0 plus u sub 0, and t is time. And the vertical velocity equals v sub 0. What is the dimension of this velocity field? The third question is about the steadiness. Is this velocity field steady or transient? The horizontal velocity equals a constant value u, and the vertical velocity is v sub 0 times cosine 2 pi over lambda times x minus uto. Is this velocity field steady or transient with respect to a moving observer with the velocity of u in x direction? Obviously, this velocity field is a function of time, but the question is with respect to a moving observer with the velocity of u in the horizontal direction. Question number 4 is about the compressibility. Is this velocity field compressible? If yes, the fluid particle experiences compression or expansion. And also, the fluid is liquid or gas. Answer these 3 questions about this velocity field. Question number 5 is about the rotationality. This is the stream function of a velocity field. Try to find the vorticity vector and judge about the rotationality of the flow. Question number 6 is about the circulation. Compute the circulation of this velocity field. These 2 counters, the radial component of the velocity is 0 and the circumferential velocity equals the constant over the radial coordinate. And the first counter is, as you see, we have a singular point at the origin. So the first counter contains this singular point, and the next one does not contain the singular point at the origin. Question number 7 is about the flow rate computation. So compute the flow rate crossing the area between 2 points A and B. A is the vertical distance of A from the origin is 1, and the horizontal direction of B from the origin is again 1. So what is the direction of the flow? Which of these 2 arrows correctly shows the direction of the flow? And also compute the volumetric flow rate between crossing the area between those points, and the stream function of this flow field is twice x squared y minus 2 over 3 y squared. Question number 8. Is this flow field Eulerian or Lagrangian? Here x sub 0 and y sub 0 denotes the initial position, and t is the time. T sub 0 is the initial time. The horizontal velocity component equals e sub 0 times e to t over t sub 0, and the vertical velocity equals y sub 0 times e to t over t sub 0. Question number 9. Compute streamlines of this velocity field. The horizontal velocity component equals 1 over t sub 0 plus t o times x, and the vertical velocity is a constant shown by v sub 0. Question number 10. Compute path lines of this velocity field. U equals x times 1 plus 2i's t, and v equals y. The answer to the first question, as you see here, I have sketched the velocity profile of this velocity field, and here we have a velocity jump just on the boundaries. Here we have a stationary wall, so the velocity should be 0. But if you compute the magnitude of the velocity at the lower wall, it yields that the velocity is non-zero. So we have a jump of velocity on the lower wall. Similarly, we have another jump in velocity on the upper wall. Here at the dimensionless distance of unity, we have something which is not equal to v. V is the velocity of the upper wall. So this velocity field shows a non-continuum velocity field, and we have discontinuity in velocity near walls. The second question is about the dimension of the velocity field. The dimension of a velocity field is defined as the minimum number of required geometrical coordinates to describe a velocity field. So here, at the first glance, we may say that we need two coordinates, x and y, so the dimension is 2. But here, if you transport this velocity field to the polar coordinate, so you'll see that you just need one coordinate, or the geometrical coordinate, which is the radial direction. So the dimension of this velocity field is the minimum number of required coordinates. So this is a one-dimensional velocity field. The next one, we have two velocity components, but in the formula you just see one geometrical parameter, which is x. So we have a two-component velocity field, but one dimension, but the dimension is 1. So this is a one-dimensional velocity. The answer to the third question about the steadiness, again, it's so obvious that this velocity field is a function of time, so this is transient. But when you describe this velocity field with respect to a moving observer with the velocity of u and 0 in horizontal direction, so you'll see that the horizontal velocity vanishes and the vertical velocity becomes a constant independent of time. So you have mentioned that always this steadiness is something related to the reference frame. So when I ask you about the steadiness of a velocity field, you have to ask me with respect to which coordinate. Here, the observer moves with the velocity of u, and so this term is 0, and cosine of this term is unity, and the vertical velocity is again 0. The fourth question about the compressibility of the velocity field. You have to compute the divergence of the velocity field. The divergence of this velocity field equals a plus a, which is not 0, so this velocity field is compressible. And again, you know that the divergence of the velocity field equals the rate of change of the volume of fluid particle over the volume. So if this is a positive number, for example, suppose that A is a positive number, a positive non-zero number, so the fluid particle, the volume of the rate of change of volume of the particle with respect to time is positive, and vice versa. And we cannot say anything about the fluid, liquid or gas. Compressibility has nothing to do with liquids or gases. Both of them can be compressible or incompressible. The fifth question is about the rotationality or the vorticity vector. This is the string function. You can compute the velocity component with using the definition of the string function, and then computing the curl of that velocity field to obtain vorticity. If that vector is 0, then the velocity field is irrotational. But alternatively, you can directly compute the vorticity vector using the string function. Vorticity equals the curl of the velocity field in two-dimensional cases. Here, as you see, we have a two-dimensional string function. So it can be proved. It's so straightforward. You can try it using the definition of the vorticity and the string function. That minus the component of the vorticity in z direction, because the fluid two-dimensional, the vorticity vector just possesses one component in z direction, equals Laplacian of psi. So you just take the Laplacian of both sides of the given relation, and also pay attention to this minus sign here, and the component of the vorticity vector in z direction equals minus twice a, so which is not 0. So, and also from the if a is a positive number, it means that the vorticity is a negative number. So in xy plane, two-dimensional plane, if the vorticity is a negative number, it means that the direction of rotation is clockwise. Question number 6 is about circulation. This formula denotes the well-known free vortex. And as you know, the free vortex is an irrotational flow field, and the vorticity of this velocity field is 0. But pay attention to the singular point of the flow field, which is the origin. So the vorticity is 0 all over the domain except the origin. You can compute the circulation directly using the original formula. This is circulation, which is a counter integral along a closed curve. The velocity dots the unit differential element parallel to the path. And using the Stokes formula, you can compute circulation using the flux of vorticity crossing the area inside that closed curve. So for the curve B, because this curve does not contain the singular point, so vorticity in all points inside the curve is 0. So using the second formula, which is a double integral over area, vorticity is 0, so integral of 0 is 0, and the circulation along this counter is 0. But for the first counter, as we do in potential flow to find strengths of point vortex, you may use the original formula, which is the dot product of the velocity and the dl, and the answer is twice pi c. This is the circulation along curve A, closed curve A. Question number 7. Compute the flow rate between points A and B, and also determine the direction of the flow crossing that line connecting two points. As you know, the volumetric flow rate in two-dimensional cases here, as you see here, with the units of square meter over second equals Q, the volumetric flow rate, equals the stream function, value of stream function at the upper point, which is A here, minus the value of the stream function at the lower point, which is B here. And just substitute 0 and 1 to find the stream function value for A, and 1 and 0 for the next one, and you can easily obtain the volumetric flow rates. Pay attention to the minus sign here. This means that the direction of the flow rate, as you see in the figure, is from the right side to the left side. If instead of the stream function, the velocity components are given, or the potential function is given, you can obtain the magnitude of the stream function, and then again repeat the solution procedure to find the volumetric flow rates. Question number 8. This velocity field is given, and you can, as you know, this is a Lagrangian velocity field because the input variables are the initial position of the particle. But all other velocity fields on the board are all Eulerian, because, for example, in this case, to find the velocity, you just need the time and the position. This viewpoint is Eulerian, but in this formula, to determine, to calculate the magnitude of the velocity components, you need the time and also the position of the particle at the initial time. Question number 9 is about streamlines to a one-dimensional velocity field. Exactly this case is given, and a transient, and you have to find streamlines. This is the formula. S is a coordinate attached to the streamline, and its origin is at x sub 0 and y sub 0, for example. And the derivative of x with respect to s equals u, and similarly for the other direction. Integrate both sides of the equation. The mathematical relations are straightforward, and substitute the boundary condition. I mean s equals 0 when x equals x sub 0 and y equals y sub 0. And this is the final formula of the streamline which passes through the point x sub 0 and y sub 0. We can see s here. And if you want to find the explicit form of the answer, you have to omit s between these two relations, and the final result is this relation. Number 10, question number 10, find path lines of this velocity field. We have a two-dimensional transient velocity field, and this time the derivative of x with respect to time should be the x component of the velocity. Here the derivative is with respect to s, but t here is time. And again, the time derivative of the next coordinate y should be the vertical velocity component, which is y here. So again, integrate, but this time with respect to time, and substitute the boundary condition, which is the point x sub 0 and y sub 0 equals 1 when at the initial time. So this is the path line of the particle which starts its motion at the initial time, or t sub 0, at point 1 and 1. Again, you may keep time in the relation. This is the implicit form. If you want to find the explicit form, you have to omit t, time, between these two relations, and the final compact form with just x and y in a relation is this one here.